have started recording now. Let me share the screen as well. Good evening to all. I welcome you all to the week 6 live session for Advanced Concrete Technology NPTEL course. Sorry for the delay. In this particular week, we will be discussing problems from week 6 content, in which the professor has explained about mineral admixtures. Okay, so can anyone say the benefit of adding mineral admixtures? At least one benefit of adding mineral admixtures to cement concrete. Sir has talked about sustainability. Can anyone say what will happen to carbon dioxide emission if you add fly ash to concrete? Okay, yeah, it reduces carbon dioxide emission because cement industry is one of the polluting industry which is responsible for about 6 to 8% of carbon dioxide emissions, man-made carbon dioxide emissions. So we have to reduce the carbon dioxide emissions due to cement production. So adding chemical mineral admixtures is one of the method to reduce the carbon dioxide emissions. Sorry, let me start the video. So now today let's enter to the problems. This is a question 1. I've already launched this question in polls. If you want the question to be entered in chat box, if you want me, I'll do that as well. Okay. So to the people who have joined new, I'll explain it. So to the bottom right corner of your screen, there is an option called activities. Okay. If you click that, you can find various options. Out of that, you have to click polls and give the answer. Okay. Already people have started giving your answers. Thank you. So if you're using a mobile phone, there will be a 3 dot, right? If you click that, you can find an option called activities. From that, you can find polls. Okay. So you have to pick the option which you find more relevant to the answer, to the question. So let me get back to the PPT. So here is the first question. The first question is based on the chemical oxide composition of the SCMs. Okay. So you have to find out the correct option showing calcium oxide content in the descending order, which will have the calcium oxide content more. Okay. So here are different options which includes Portland cement, silica fume, type of fly ash and GGBS and metakaolin as well. So you have to think which has more calcium oxide content. Okay, so let me fix the timer uh, for a minute for this question. So after a minute, we'll discuss the answer. Okay. If you guys not able to give the answer in polls, please give your answer in the chat box. I start the timer for 1 minute. After 1 minute, we'll see the answer. If you guys have gone through the lecture PPT, this is a very easy question. So just think what is type of fly ash and what is type C fly ash. Are they both same, which has more calcium oxide? Just think about it and then answer. GGBF is nothing but ground granulated blast furnace slag. Time is up. Let me stop sharing the screen. Let's see the answer you guys have given. Okay. Only 3 people have given your answer in polls. Okay. Then chat box. No one has given the answer. Okay. Is this question very difficult? Okay, from next question is going to be true or false, so everyone should give your answers. Okay, so let me end the poll for question 1. So, and we'll discuss the answer for question 1 then. It's option C. Okay, let's see what is the right answer. So here is the chemical composition. This I took from the lecture PPT, which is shared with you as well. So here this shows that out of all, Portland cement has around 65% calcium oxide. So it will be usually uh, uh, 60 to 70%. Sorry for disturbing all. I have a call that I have to pick up. Hello. Okay. Sir, I'm in live session. Sorry. Thank you. Sorry. So uh, Portland cement has the highest calcium oxide and followed by GGBS, then class C fly ash, then class F fly ash, then silica fume. Silica fume will not have any calcium oxide. It has more than 90% of silica. So the correct answer is nothing but option D. So because Portland cement has the highest amount of calcium oxide, around 60 to 70%, then following by GGBS around 40 to 50%, and then coming type F fly ash, which will have very less calcium oxide, then silica will not have any calcium oxide. Okay, so the correct answer is option D. Yes, sir. Sorry, I met with an accident. Sorry, we should not discuss about this during the class. Yeah, I'm managing, sir. I'm recovering. Okay, sir. Okay, sir. Thank you, sir. Let's move to the next question. So, if you guys have any doubt by any point of time regarding the question, please stop me by any moment. We'll discuss. Okay. So even after all the questions are over, we can stop by and we can discuss any queries you have. Okay. So now moving to question 2. I've already launched this question in polls. Uh, Please give your answer in polls. If you are not able to give it in polls, please give your answer in the chat box. The question is, the unburned carbon extent in fly ash is determined by loss on ignition test. So let me start the timer now for a minute. After a minute, we'll see the answer. So here they are saying we have to do loss on ignition test for fly ash to find out the unburned carbon extent. Is it true? It's very easy question. Either it's going to be true or false. Please give your answer. At least for this, everyone should give your answer. Okay. It's not confusing. It's either going to be A or B. Unburned carbon extent means some of the fly ash will not be completely burnt. Sorry, coal will not be completely burned, and it will be remain as unburned carbon particles. So the time is up. Let me stop sharing the screen. So more votes for true. Okay, let's see. Okay, more A options. Let's see. So most have given the right answer. So the correct answer is true, because loss and ignition test is directly from the slides. I took it from the lecture PPT. The loss and ignition test is done for all the SCMs. We can do it for fly ash, rice cash. So it will be burned to 700 to 1000 degrees Celsius for 2 to 3 hours. It depends upon the SCM and the code we follow. Either it's from SCM code or IS code. Based on the codes, the time and temperature might vary for the SCMs, and then it will be burnt at muffle furnace for a given time, and then we'll measure the weight difference. So that gives the unburned carbon extent in the fly ash. So it's true. It's a very simple question. So the next question is, the ball bearing type effect of fly ash particles decreases workability and flow of concrete. Here they're saying that fly ash has a particular effect called ball bearing type effect because of its particle size. Okay, sorry, particle shape. Because of the particle shape, it has a ball bearing type effect which decreases the workability and flow of concrete. Okay, let me start the timer now. After a minute, we'll see the answer. Even after giving solution, if you're not able to understand or if you have any query, please stop me by any time and then we'll discuss. This particular problem solving session is for you to encourage to participate in the weekly assignments and then help you to score more as well. Yeah. Time is up. Okay, let's see the solution. Can someone say what is the particle size, predominant particle size of fly ash? Is it spherical or triangular or platelet type of structure? What is the shape of fly ash? What is the shape? What do you expect? I think sir has also discussed about this in the uh, lecture about the particular shape of fly ash, and it's helping in certain extent, and then which is not in the case of rices cash. I don't think that you guys have this particular content has covered rices cash. Okay, let's stop it to fly ash then. Okay, more option for A. I don't know whether it's for question 1 or question 2. Let's see. The polls. Okay. Let me end the poll for question 2. Question 3. Okay. Both true and both false. And I've seen more option A in the chat box as well. Okay, let's see then. So getting back to the what is the effect of fly ash on the fresh property? Because workability and flow of concrete is nothing but the fresh property of concrete, and strength is nothing but the hardened property of the concrete. Okay, so effect on fresh concrete. So the setting time is okay. I think this is going to be a problem for the next question. Okay, so the coming to workability and flow of concrete are increased due to the spherical shape of the fly ash particles, which lends a ball bearing type effect on the concrete mixture. So which means, so the fly ash particles are more or less spherical in shape. Okay, so which gives a ball bearing type of effect, which makes the fly ash to flow easily. So it increases the workability and flow of the concrete. So the correct answer is false, because they are saying that it decreases. It does not decrease, it increases the workability. Okay. Moving to the next question. So the question 4 is, it's a bit complex question. So I'll read out the question and I'll explain you. And I could not put the complete question in polls because there is a limitation to 300 letters or 300 letters. So I could not complete the question in polls. I'll read out and I'll explain the question. So here is the fourth question. The pozzolanic reaction leads to pore refining because of the conversion of a crystalline material to a semi-crystalline amorphous material. Okay, so let's assume that cement undergoes hydration. Okay, what are the hydration products formed? Can someone say what is hydration product if cement gets hydrated? Normal OPC. Okay, CSH. This is one of the, it's a major hydration product. Next. CH, yeah, Portlandite is one of, Portlandite is the is also a reaction product. And then what does the aluminate phases react to form with calcium and silicate? That is calcium aluminate hydrate. If gypsum is not there, it will form mostly, but if gypsum is there, then it will form ettringite and monosulfate phases. Okay, so it's called AFM. AFM means monosulfate and AFT means ettringite phases. So it will form CSH, Portlandite, AFM and AFT phases. So calcium aluminate hydrate will form if a sufficient amount of sulfate is not present in the cement. But we generally add 4 to 5% of gypsum in Portland cement, right? Ordinary Portland cement. So there will be enough gypsum, so it will form AFT and AFM phases. So here they are saying the Pozdonic reaction leading to pore refining because of the conversion of a crystalline material to a semi-crystalline amorphous material. They are saying that out of the reaction products, one particular reaction product possesses a crystalline form. It's not amorphous. For you to make it easy, I'll say CSH is a semi-crystalline to amorphous kind of material. So here they're saying conversion of a crystalline material. Okay. So just think you can avoid CSH and then think about rest of the hydration products to a semi-crystalline or amorphous material. This conversion of a crystalline material leads to interface refining, particularly ITZ zone. Okay. As it is present in larger amounts at the interface. Okay, they are saying there are more space available for this particular hydrates to form in the interface, ITZ. Okay, further, the conversion of this crystalline material to amorphous material, they are saying that initially the product will be crystalline material, and due to since we are adding pozzolanic material, pozzolanic reaction happens between the amorphous material and the like reactive silica will be from the pozzolanic material that reacts with this crystalline material from OPC hydration, and it forms semi-crystalline material. Okay, so further the conversion of this crystalline material to amorphous, that is amorphous material, leads to increase in possibility of carbon-induced corrosion. They are saying since the conversion of this crystalline material to amorphous material, it increases the possibility of carbonation, carbon-induced corrosion. This crystalline, that is one, you have to find the crystalline material and the semi-crystalline amorphous material formed. So you have to find what is the crystalline material initially formed out of OPC hydration and find out how does it convert on pozzolanic reaction to a semi-crystalline or amorphous material. That is option 2. Okay, let me start the timer now for a minute. After a minute, we'll see the solution. If you guys have any doubt, please stop me by any time. We'll discuss and I'll clarify you again. Time is up. Do you guys still need time for this question? Okay, let me stop sharing then. So, coming to question, only one person have given answer in false. Okay, option B then. No more answers. Oh, this question is very difficult then. Okay, let's discuss then. Like how many of you not able to understand the question? You can rise up or put one in the chat box so that I'll know that you guys are not able to understand the question. Or you can raise your hand. I'll know. Okay. Let's get into the solution then. Someone had told me that the reaction products formed on OPC hydration are CSH, Portlandite, AFT and AFM phases, that is yttringite and then monosulfate phases, right? So that you will get to know once 7 chemistry chapter you have gone through the videos, then you will get to know what are the type of reaction products formed on OPC hydration. And here they are saying crystalline material. So out of all these phases, Portlandite is a crystalline material. So that is like which reacts on pozzolanic reaction. Is a crystalline material that reacts on pozzolanic reaction to form a semi-amorphous material, to form a semi-crystalline or amorphous material. So we can rule out the first option. And coming to B, C, D, uh, here we have to find out what is the next option. Here also it is CH and slash CH, so we can rule out this option as well. And coming to B and D, both option 1 and 2 are same. CH is nothing but Portlandite, so we can rule out option D as well. So the correct option is option B. Okay, so I request everyone to mute yourself. If you have something to discuss, please unmute. Okay. Okay. Sorry for the disturbance. So now getting back to class again. So can someone explain pozzolanic reaction to me? What is my pozzolanic reaction? Like, okay, yeah. So, yeah, as you said, so let me have a pen here. So, as I said, initially there will be CSH and then this is the primary reaction product. Then there will be Portlandite. I'll write as CH and then next is AFT and AFM phases. Let me write it as AFT and then AFM. Okay, so okay, so majorly C3S and C2S, no tricalcium silicate and dicalcium silicate reacts with water to form CSH and then CH, Portlandite as well. So remaining the tricalcium aluminate and tetracalcium aluminoferrate reacts with existing water and then sulfates to form AFT and AFM phases. Okay. So coming to CSH and CH, CH is the crystalline product remaining mostly in the interfaces because it needs more spaces, it requires more space. So mostly in the interface we'll find more space between the aggregates and the concrete. Okay, that is the interfacial zone, interfacial transition zone, ITZ. So we can find more Portlandite in the interfacial transition zone. Okay, so that is a major point where if concrete is subjected to chemical attack, so first it will attack the hydrates in the interfacial transition zone because it has more space to for the liquids to enter. Obviously, Portlandite will be there, that will be readily available for reaction. So that will react with the coming to sulfate attack and all that will be discussed in the following lectures. So the environment, if the aggressive environmental, if some aggressive chemicals comes from the environment, then it will react with this particular phase, Portlandite, and it will affect the concrete durability. Okay, it will affect the concrete performance. So what happens the pozzolanic reaction is this Portlandite reacts with the amorphous silica with the pozzolon, either it's coming to uh, fly ash or silica fume or GGBS. We have reactive silica in it, so that's amorphous silica that reacts with this Portlandite to form CSH. Okay, so that further refines the pores and it fills the pores, so that so it increases, it causes pore refining and it increases the resistance for the chemicals to enter the concrete. So it reduces concrete permeability. So it's very helpful. So CH converts into CSH if the reactive pozzolan has more reactive alumina as well. Like if it's a calcine clay, it will have reactive silica as well as reactive alumina. So in that case, it will form calcium aluminate hydrate as well. Okay. So predominantly it forms CSH only because most of the pozzolans will have reactive silica and then as well as reactive alumina. Okay. Can everyone understand the question and the answer? So here is the snap from the slide is from the lecture. So here they are saying outer CSH and inner CSH, in between there is aggregate, and uh, like if mostly in between aggregate there will be more spaces in the ITZ. So there this portlandite will be formed. That portlandite will be readily available for the chemicals to react with the chemicals from the environment, like sulfate from the environment. From soil we can have sulfates, right? From the, like if it's near agricultural field, then it will have more gypsum. So such things will come and react with the portlandite to form uh, uh, pro, uh, like sulfate reaction products that will affect the durability of the concrete. That will be taught to you guys in the later stage of the course. Okay. I don't want to make it more critical for you to understand this question. If someone is not able to understand, you can unmute yourself and ask now, or else we can discuss this after all the questions are over. So here this portland will be converted into CSH. Okay, I hope you got it. If you move to, so the correct answer is option B. Now let's move to question 5. I've already launched this question in polls. Please give your answer in polls. Let's move fast by then. I've made so much time for that particular question. The question 5 is silica fume addition reduces water demand for the mixes. Let me start the timer. It's very simple. Water demand in the sense to attain a particular flow. Uh, yeah, to fix the water to cement ratio, we generally do flow test and check the water demand, right? To check the water demand, we do flow test. To attain a particular amount of flow, we need to add. That should be if you're not able to attain a flow by 0.4 water to cement ratio, we can increase it to 0.5 or 0.45 to increase the flow. So here they're saying if you add silica fume to cement, it will reduce the water demand of the mixes. They are saying like that. Do you feel it is true or false? And to add, silica fume is a very fine material, and we have to densify it to transport, and then again we have to mix it for a long time to while preparing the concrete. For addition, we have to mix it for additional time than normal concrete. Okay, let's see your response. Not much answer I could find in polls. No one is typing. Maybe everyone started using polls then. Okay, chat box is working. Me in the poll for this question. Silica fume addition reduces water demand for the mixes. Yeah, it's false. Because silica fume is a very fine material. So addition of silica fume to the cement will obviously increase the flow, because if you increase the specific surface area of the material, fine materials will have more specific surface area. So that will increase the water demand. So it's already given in the lecture as well. Effect of silica fume addition on fresh concrete. So because of its high fineness, use of silica fume usually causes increase in water demand. So typically, if you are using silica fume, we'll go with a super plasticizer to reduce the water demand. Okay. Now let's move to sixth question. The question 6 is fly ash addition increases setting time of concrete. I've already read out this part when I was speaking about the ball bearing effect. So I hope you know the answer. Let's wait for a minute then and we'll discuss the answer. They are saying if you add silica fume to the cement concrete, they are saying the setting time will increase. Is it so? Please give your answer in chat box. Polls, if you are not able to give the answer in polls, please give your answer in chat box. It's very easy. Either it's going to be A or B. Not much confusion will be there. I request everyone to participate to give the answer. Time is up. Let me stop sharing then. We'll see the answer. So, okay. 5 votes for increase in setting time. That's true. Yeah. Fly ash addition increases the setting time of concrete. We'll see the solution then. So, because high replacement of fly ash, if it's going to be 5% or 10%, it will not affect much. If it's going to be more percent, like if it's 20% also, it will not affect much. If it's going to be like 30 or 40%, obviously it will affect the setting time. Okay. So here in this graph, here let me use a pointer. This is from the lecture as well. So this is the setting time. This blue line here is this a setting? This is setting time for cement only, and then the following things are for addition of fly ash. Obviously with fly ash addition there is increase in the setting time, and then we'll see 40% fly ash with 5% limestone, and then we'll compare only 40% fly ash for this moment of time. So if we add 40% fly ash to the concrete, then obviously there is increase in setting time. Even a cement concrete is set by some 4 to 5 hours. With addition of fly ash, it does take up to 7 to 8 hours. Okay, so if you have 40% fly ash but you have added 5% limestone in that case, then obviously the setting time will decrease. See, it has decreased when you have added limestone, and then with 10% limestone it has further decreased because limestone has additional sites for the CSH2 form. It will have additional reactive sites, so the formation of CSH will be more with more with the addition of limestone. Okay, so from here we'll move to the next question. This is also going to be true or false question. So here they're saying anthracite coal requires a lower temperature for burning than lignite. Here there are as per the lecture there are 5 different types of coal, and lignite is one type of coal and anthracite is one type of coal. So yeah, they are saying that anthracite requires lower temperature for burning than lignite. Okay, so I've started the timer already. After a minute, we'll see the solution. Please give your answer in polls. I request everyone to give your answer in polls. If you're not able to give, please give your answer in chat box. Time is up. Let's see the solution. Let's see what answers you guys have given. So, okay, mixed response, both true as well as false. Okay, in chat box, let's see. Okay, okay, A in the sense we think that it's true. Okay, and false as well. Okay, let's see. Have take a snap from the lecture. In that there are 5 different types of coal based on the purity. If it's a pure coal, then it's called 92, 95% pure coal is anthracite. It will have 90 to 95% carbon. If it's a semi-bituminous coal, it will have. It is also okay, but it will be around some less than 90%. And bituminous coal is 80 to 90%. Oh, my mouse pointer is okay. Bituminous coal has 80 to 90% carbon, and then say sub-bituminous coal has 70 to 80% carbon, and then lignite has it has more impurities compared to this bituminous and then anthracite coal. Okay, so here they are saying anthracite is very hard coal, and it requires high temperature to burn it. So the answer is false. So there was a mixed response. So anthracite is a pure coal. It has more carbon in it, so obviously it will require higher temperature because of its because it's a hard coal. And generally, lower rank coal will have more impurities such as clay, quartz, and all. So this impurities uh, make up the composition of the coal. Uh, like if it is only going to be anthracite, then we'll have very less amount of ash remaining, and then mostly this sub-bituminous coal range will have more impurities like clay. Then only we'll have reactive alumina in it once, reactive alumina as well as reactive silica once it is burnt. So we'll have very less ash content if we burn anthracite compared to lignite and sub-bituminous coal. So these impurities make up the composition of the fly ash that end up in the thermal power plants. Okay, now let's move to question 8. Question 8 is the reactivity of fly ash does not depend on the particle size and amorphous silica content. So I think everyone know, I've seen at least XRD plot of fly ash at least in the lecture PPT. So here they're saying the reactivity of fly ash does not depend on the particles in the amorphous silica content. Is it so? Let me put a timer for less than a minute. So after less than a minute, we'll see the answer. Please give your answer in polls or chat box. How do we say a fly ash is reactive? What is the chemical composition in fly ash that is responsible for reactivity? Just think about it and give your answer. Okay, time is up. Let's see your response. So I hope you guys got the correct answer for question 7. Let me end the poll. Coming to question 8. Okay, so again a mixed response. True as well as false. Okay. Any person in chat box? Okay. Not much answer in chat box. Okay. Let's get back to the PPT. So the answer is false because I hope I have not added any any slide from the lecture. Let me draw. Sorry. Okay. So if you see a XRD plot, so let me assume this is 10, 20, and then 30. Okay. Let me write it as 10, 10, 20. Oh, sorry, we could not write 20 exactly. And then coming to this is 30. Sorry for the poor writing and drawing skill. So, what happens is usually there will be some small peaks here and there, and then some quartz peak will be there around 26 degree here and there. So there will be amorphous hum between this 20 to 30 degree. What does this amorphous hum tell us? Can someone say? Sorry. Has anyone seen the XOD plot of fly ash before? Okay. So if you see an X-ray diffraction plot of fly ash, there will be an amorphous hum between 20 to 30 degree, which means the amorphous hum indicates the amount of amorphous silica content present in it, which is mainly responsible for the reactivity of fly ash. So here they have said reactivity of fly ash does not depend on particle size and amorphous silica content, which is false, because this is the main particle that you know about the Pozzolanic reaction happens once we add pozzolan to ordinary Portland cement, right? So this amorphous silica reacts with the Portlandite on OPC hydration and forms additional CSH. So this statement is false, and then increasing the particles is obviously increase the uh, specific surface area available for reaction. So increasing the particles will also increase the reactivity, and primarily the reactivity will be due to amorphous silica content. So this statement is false. So if you see the XRD plot of fly ash, you'll see an amorphous hum from 20 to 30 degree, which indicates the uh, reactivity of fly ash, which indicates the presence of amorphous reactive silica in it, and which is responsible for the reactivity. Okay, now let's moving to question 9. So here is the statement: heat of hydration gets lowered with the usage of pozzolanic additives. Okay, they are saying heat of hydration. I think with the lectures you will get to know we can measure the reactivity of cement and pozzolanic blended cements with heat of hydration measurement. Here they are saying with heat of hydration study, if you see with OPC with pozzolanic additives, they are saying heat of hydration will get lowered with addition of pozzolanic additives to ordinary Portland cement. This is the statement. Tell whether it's true or false. Let me start the timer now. After a minute, we'll see the solution. So, can someone say reaction of cement with water is an exothermic reaction or an endothermic reaction? Okay. If cement exothermic reaction means release of heat, and endothermic reaction means it absorbs heat from the environment. If cement is mixed with water, I think even the BTech students in your lab, you would have done this experiment to find the setting time and all. So once you mix cement with water, what will happen? It will release heat or not? Okay. Once you mix cement with water, there will be sudden release of heat. Okay. So, and it on further hydration, the heat will further will be produced because of the exothermic reaction. Let me stop the timer now. So we'll measure that heat. We can measure the total heat as well as the rate of heat release on cement reaction with water. And if we add pozzolanic additives to the cement, what will happen to this heat of hydration? Whether it will decrease or decrease. Let's see. Let's see your response and see the solution. Oh, yeah, most people have tell, yeah, it's exothermic reaction. Thank you. Okay, some people have given answer as B. Maybe it's for the last question. Let's get through the polls. Yeah, it's true. Yeah, thanks for the response. It's true. Now let's get into the PPT again and move fast. Still, we have 3 more questions to discuss. Okay. So, because this particular graph shows the heat of hydration evolution with fly ash addition. So, this black solid line is the heat of hydration for cement paste, and then the following things shows the following dotted lines indicate the heat of hydration for cement with 20% fly ash addition, and then 35%, 50%, 65%. And we can see that with increasing the by increasing the substitution of fly ash, we can see there is a decrease in the rate of heat evolution. So which indicates that using pozzolanic additives will lower the heat of hydration. Can someone tell me, unmute and tell me, can we see a similar response with silica fume as well? What will happen to the heat of hydration if we add silica fume? Will the heat of hydration increase or decrease? And normally we limit the addition of silica fume to 10%, 10 to 15%. We will not use not more than 10 to 15% in cement concrete. Okay, so silica film is a very fine material and it's very reactive because of its and it has more than 90% amount of silica in it. So obviously you can see, and it's a very fine material. It has its fineness is very small compared to cement. So obviously the heat of addition will increase when it comes to silica fume. So this pozzolanic additives normally we tend to address it as fly ash. So the statement is correct, but if it comes to silica fume, the heat of addition will not reduce, it will increase. Okay, now let's move to question 10. So here is this assertion and reasoning. So the statement here is definite crystalline peaks are obtained when X-ray diffraction is performed on GGBFS samples. Okay, here they are saying crystalline peaks are obtained when X-ray diffraction is performed on GGBS samples, and the reason is the rapid quenching of molten slag results in the formation of amorphous material. Okay, so here are the 5 options. Please give an answer in false. Let me start the timer now for a minute. So here they are saying first option is they are saying assertion, desertion, both reasoning, both are true, and then reasoning is not is not the proper reasoning for assertion, and the reasoning is proper for the assertion. And then coming to option B, here they are saying both assertion and reasoning are true, but this reasoning is not properly explaining the assertion. Okay, and coming to option C, they're saying assertion is true but reasoning is false. And coming to option D, assertion is false but reasoning is true. And fifth option says that assertion, reasoning both are false. Please go through the statements clearly before giving the answer. Do you think whether we'll get a definite crystalline peak on doing X-ray diffraction GGBS samples? GGBS is nothing but ground granulated blast furnace slag. Okay, time is up, but let me wait for 10 more seconds, or I'll show this graph here. So before I've talked about X-ray diffraction plots for let's see for low calcium fly ash, it's class F fly ash. So here we can see some this degree is 17 and this is 21 and this is 30. Okay, so we can see the amorphous sum that exists between 20 to 30, right? This is responsible for the presence of amorphous silica, and we can find the peaks that is mainly because of the presence of quartz in fly ash, quartz. Okay, and moving to GGBS, can we see any crystalline peaks here? No, right? Is the assertion true? No, right? It's false. So coming to GGBS X-ray plots for GGBFS, we will not find any crystalline peaks unless if it's air cooled. Okay, if it's quenched, obviously it will not have any crystalline peaks. Mostly, if it's a quenched, rapid quenching slag has more reactivity because it will have more amorphous chemical composition, amorphous structure. And then if it's air cooled, if the GGBF is if it's air cooled, then obviously crystalline peaks will be found. Okay, so if possible, please check out what is the X-ray. Check out the X-ray diffraction plots for air cooled slag as well as rapid quench slag. Then you'll get to understand. Sorry, I would have put it here, but I forgot to put and differentiate between air cooled and as well as rapid quenched slag. So, and reasoning says that rapid quenching Rapid quenching of molten slag results in the formation of amorphous material. That is true. So obviously the answer is, assertion is false but reasoning is true. Uh, let me check your response after some time. So let's move to question 11. So coming to question 11 and 12, you should give the answer in chat box. You can't give the answer in polls. Let me read out the question and then we'll start the timer. So you have to find the true statements. Okay, which of the following statements are true? It has more than one option. That's why I not launched the question in polls. Please give your answer in chat box. The first statement is the reactivity of slags produced by quenching and pelletization are different. Just before I've discussed, so you should find out the right statement. Okay, they're saying the reactivity of slag produced by quenching and pelletization are different. Okay. Then option B is reactivity increases as the crystallinity of the material increases. Just think either amorphous material will be reactive or crystalline material will be reactive. And moving to option C, quartz and mullite are the amorphous silica phases present in type F fly ash. I just told quartz will be present. If quartz is present, there will be peaks, and if there is a peak, will it be an amorphous or crystalline material? Just think. They're saying quartz and mullite or amorphous silica phases present in type of fly ash. And then option D is class C fly ash exhibits both pozzolanic and latent hydraulic nature. So to give a small clue, class of fly ash will have at least 18 to 20% of at least 18% of calcium oxide in its chemical composition. So let me start the timer now. After a minute, we'll see the solution. Please pick out the true statements, which is correct. Let me stop sharing. It's already 7:02. So let's see your response and then yeah. So no answers at all. Okay. Oh, okay. That produced by quenching. Okay, let me take this as true. Okay, let's see the solution. Then I hope you guys are tired by now. So the correct statements are option A and D because reactivity of slag produced by rapid quenching and then pelletization are different. Yeah. And then reactivity increases as the crystallinity of the material increases. That's not true. If the amorphous content increases, obviously the reactivity will increase. The presence of amorphous silica will increase the reactivity of the pozzolana, say if it's fly ash. And moving to quartz and mullite or the amorphous silica phases. That's not true. Quartz and mullite are crystalline phases. And then coming to option D, Class C fly ash exhibits both pozzolanic and latent hydraulic nature. Yes, GGBS as well as Class C fly ash will have more calcium in it. Class C fly ash should have more than 18% calcium oxide in it. Will have around 18 and more than 18% calcium oxide. And coming to GGBFS, it will have around 40 to 50% of its composition as calcium oxide. So if there is calcium in the system, obviously it will exhibit both pozzolanic as well as latent hydraulic nature. If the calcium oxide to silica ratio is around 1, then obviously it will exhibit both latent hydraulic as well as pozzolanic reaction if it has reactive silica in it. Okay. Now let's move to question 12. This is going to be a match the following question. It's very simple as well because here you have to just find out what is normally pozzolanic. out of these options which is normally pozzolanic, and then what is latent hydraulic, and then which will have calcium to silica ratio in the range of 2 to 2.8, then what is weak pozzolon out of these options. I've just explained uh, GGBFS and class C fly ash have calcium in it, so it exhibits both response. So please give your answer in chat box. Let me see the response later. Let me start the timer for a minute and then we'll see the solution. Maybe if you're able to match one or two also, it's fine. So if the calcium to silica ratio is very less, okay, if it's very less, then it's called normally pozzolanic, that type of pozzolon. So if it is in the range of calcium to silica ratio is in the range of close to 1, then it is latent hydraulic. Okay, now let's see the solution. So the correct answer is normally pozzolanic is nothing but class F fly ash because it has very less calcium in it, so it is normally pozzolanic. And then latent hydraulic is nothing but GGBFS because it has calcium to silica ratios in the range of 1, close to 1. And then Portland cement, hydraulic cement has calcium to silica ratio in the range of 2.8. And bottom ash is a weak pozzolon because the amorphous silica content in it will be very less compared to fly ash. Bottom ash has less percentage of reactive silica compared to fly ash, and then it has more unburned carbon fraction in it compared to the fly ash. Okay, so it's a weak pozzolon. So now I hope you guys followed this and found it helpful. So yeah, I could see the answers here. Okay. I hope you guys got the answer as well now. So let me wind up the session here. If someone has any query, I can stop by and respond to your queries. Does anyone have any query? Okay then. Thank you for your active participation in the polls as well as chat box. Yes, sir. Uh, Mostly today you'll get the content today. Yeah, yeah. Today it will get updated. Yeah. Okay, then let me close the session by now.